This video we're going to talk about electrolytic cells. So an electrolytic cell is made of electrolyte, so that would be an ionic solution or a molten ionic compound, a battery or some sort of power source that would generate electricity, two electrodes, either carbon or an unreactive metal, and the anode is attached to a positive terminal and will attract negative ions, and the cathode is attached to the negative terminal and will attract positive ions. And then when the ions reach the anode or the cathode, they'll either be oxidized or reduced and then discharged. So the ions move in a certain direction when an electrical field is applied to a molten or dissolved ionic compound. And you can actually see this in experiments where you use colored salts. So we're going to use copper 2 chromate 6, and it will change color at the presence of the graphite cathode or the graphite anode, because the ions, the copper 2 ions, will move to one and the chromate ions will congregate in another, which will change the color in the presence of the hydrochloric acid. So we use this copper dichromate, which is green, and we put it in a U tube. It's a tube that's shaped like a U, with dilute hydrochloric acid placed on top. The graphite rods are inserted into each end of the U tube, and an electrical current is applied, and the cathode solution will turn blue and the anode solution will turn yellow from green. And this is because the copper ions are being attracted to the cathode and the dichromate ions are being attracted to the anode. So when we look at molten ionic compounds, an example of this type of electrolysis is using molten lead 2 bromide. So in this equation, the lead 2 bromide is splitting apart into lead and bromine, gaseous bromine. So you can see the bromine vapor escaping here, and then the lead is actually becoming liquefied. So the anode is positive. So because it's positive, the negative bromide ions are going to accumulate here. And this is the reaction. So the 2 bromide ions become bromine gas and 2 electrons, so the gas or the vapor will escape. And then the lead 2 plus ions are attracted to the negative cathode, and you have lead 2 plus 2 electrons makes lead. So you have your liquefied lead arriving there. So this is an example when you can actually separate the lead 2 bromide into liquid lead and bromine gas. So using electrolysis. And we use electrolysis for a lot of things. It's a way of separating compounds into their individual elemental states. We'll spend more time talking about that in our higher level material in a later lesson. So if we were to compare voltaic cells with electrolytic cells, there's a few things that happen. So a voltaic cell, the oxidation occurs at the negative anode. In the electrolytic cell, the oxidation occurs still at the anode, but the anode is now positive. And then in a voltaic cell, the reduction occurs at the positive cathode. Reduction occurs at the negative cathode for an electrolytic cell. In a voltaic cell, it's an exothermic spontaneous redox reaction. However, electrolytic cells, and we'll learn this in our later lesson, it's actually an endothermic, non-spontaneous redox reaction. We have to apply an electrical current to make the reaction happen. It's not going to happen on its own. It will not be spontaneous, ever. In a voltaic cell, cells convert chemical energy into electrical energy, and in an electrolytic cell, we're using the electrical energy that's being applied to the cell, and we're using it to split things apart and create chemical energy. In a voltaic cell, the cathode is positive and the anode is negative during the discharge, whereas it's the opposite in an electrolytic cell. So the cathode is negative and the anode is positive during electrolysis. In a voltaic cell, we have those two separate aqueous solutions connected by a salt bridge and an external circuit, whereas the electrolyte in the electrolytic cell is a molten liquid or an aqueous solution. And then finally, the electric current is conducted by the electrons in the external circuit and the movement of ions in the salt bridge. So that's how you get your current to flow. Sometimes if you forget to put the salt bridge in, you don't get a reading at all because on your voltmeter, because there is no means of the ions moving. So the circuit isn't complete without the salt bridge. And then in an electrolytic cell, the current is conducted by the electrons on the external circuit and the movement of ions in the electrolyte. So in this practice example, we're to deduce the half reactions for the following cell. So we need to take a good look at it. What type of electrolytic cell is it? It's a molten zinc bromide. So this is an ionic compound that has been melted. So it's at high temperature. So it's melted to be liquefied zinc bromide. Over here is our anode. So that's where the bromide ions are accumulating. The zinc ions are accumulating over here. So remember, the bromide ions, if they're accumulating at the anode, that means that they're being oxidized. So we're going to write that down. So we have our bromine liquid form. So it's been split apart using heat. And then that becomes bromine gas. And it's going to be released into the air. And we need to balance this, so we need to put a 2 here. And it's lost its 2 electrons, so 2 electrons. And then at the cathode, we're going to have our zinc 2 plus. And that's liquefied. And we have our 2 electrons because it's being reduced to become zinc liquid. So our overall equation, if we were to write that out, would be zinc bromide liquid becomes zinc liquid plus bromine gas. So there's our equation. So the molar ratio of products is 1 to 1. So those are our half reactions and our overall equation.